Hello everybody. In the last session we had discussed about the constructional features of three-phase synchronous generators or alternators. Today we will look at the relationship between speed and frequency. Consider an alternator whose rotor is being driven at a constant speed of n rpm. Suppose if there are p number of poles and let f be the frequency of induced EMF. In one complete revolution of the rotor, each of the north and south poles move past all the stator conductors. So that means, suppose if this is the conductor and this conductor moving is expected to be at this point stationary, and this rotor is moving, and this rotor is moving past the conductor in one rotation. Suppose if there are p number of poles, in one rotation of the rotor there will be p by 2 cycle of EMF is induced. So that means when one pair of pole move past the armature conductor, induced EMF undergoes one full cycle. Therefore, in a p-pole machine, in one complete revolution of the field system, the induced EMF in the armature conductors will complete p by 2 cycles. Number of cycles of EMF induced per second is given by number of cycles per revolution into number of revolutions per second. That is, frequency in cycles per second or hertz is given by p by 2 into n by 60. Finally, the expression for frequency of the induced EMF is given by Np by 120 hertz. So let us look at more about armature conductors and armature winding coils. Armature coils can be of single turn coil or it can be multi-turn coils. In single turn coil, only one turn is involved. So you can see here, this is the starting end of the coil, this is the finishing end of the coil, and this portion of the coil is called as conductor, and this portion is actively involved in energy transfer because this part of the coil, the conductor, which is under the influence of north pole or south pole, and this conductor is subjected to change of magnetic flux, and because of that EMF is induced in this part of the armature coil. This part of the coil is called as back connection. This is not participating in energy transfer. However, this provides the connection between two conductors placed under different poles, and this completes one turn, and this portion is also called as conductor and also coil side. So for a single turn coil there are two coil sides, and each coil side will have only one conductor because it is a single turn. And in the case of multi-turn coils, we will have many turns. So this is the starting end of first turn, and it is wound like this, completed one turn, and there will be several such turns constitute multi-turn coil, and finally the wire what is leading out is shown here. So this is a multi-turn coil and this is a single turn coil, and for both of these coils there is a coil span. Coil span is the distance between two conductors of the coil measured in terms of armature slots. Coil span or coil pitch. Pitch of the coil is the distance measured in terms of armature slots between the two sides of a coil. Suppose these are the two sides of the coil and this is the coil span, and the two coil sides of the coil are expected to be under the influence of two different poles. So that means suppose if one side of the coil is under the influence of north pole, other side of the coil should be under the influence of south pole. So this being the case, the induced EMF what is induced in the conductors of this coil side and the conductors of the other coil side, and they are in phase and the total EMF is being additive. Suppose 1 volt is induced per conductor here and there is 1 more volt induced here. So, the net voltage for 2 conductors will be 2 volts. As far as pole pitch is concerned, we can have more discussion about pole pitch. The inner periphery of the armature consists of number of slots. So, you can see here, this is the inner periphery of the armature or the stator core, which has large number of slots as shown, and total number of slots in this particular example is 36. And suppose if the stator is designed for 6 poles, then pole pitch is given by 36 divided by 6 is equal to 6 slots. So, total number of slots divided by the number of poles of the generator is termed as pole pitch. Pole pitch can also be defined in this fashion. The center to center distance between 2 adjacent poles, adjacent poles are north pole and south pole, in terms of armature slots is called as a pole pitch. At any point of time, see in this example, there are 6 slots under the influence of any one pole. So, number of slots under the direct influence of north pole is shown here, and next is south, then alternatively north and south. So, this is at any one point of time, and at different point of time, since the rotor rotates, the number of slots under the influence of any one pole remains the same, but the very slot what is shown here will be under the influence of north and south and again north and south alternatively, because this rotor what is inside the stator is on rotation. So, let us see what is meant by slot angle. Angle of slot in electrical degrees is called as a slot angle, and it is denoted by beta. So, beta is given by 180 degree divided by slots per pole. So, why this 180 degree? So, because one pole is responsible for 180 degree electrical, and when the conductor move past between 2 poles, then one cycle of EMF is induced. So, 180 degree means half cycle of EMF corresponding to slots per pole, that is 6. So, slot angle is given by 180 degree divided by number of slots under the influence of each pole, that is 6. So, which is in this particular case 30 degree electrical. So, let us compare the difference between full pitched and short pitched coils. Suppose the coil span is shown here. Coil span is equal to pole pitch, then the coils are said to be full pitched coils, and the coil span in terms of electrical degrees is equal to 180 degree electrical. So, for full pitch coils, in a example what is taken earlier, suppose if there are 36 slots and 6 poles for a alternator, coil span for full pitched coils is equal to the pole pitch, and pole pitch is given by 36 divided by 6, which is equal to 6 slots. In the case of short pitched coils, if the coil span is less than pole pitch, then we term such a coil as a short pitched coil, and coil span can be less than 180 degree electrical. For example, in the same case 36 slots and 6 pole alternators, if coil span is less than pole pitch by say 1 slot, then coil span instead of earlier 6 slots, now it will be 5 slots. So, 5 slots, or if the coil span is shorted, in short of 2 slots, then coil span becomes 4 slots, and it is 4 slots means each angle, slot angle is 30 degree, 4 slots means 120 degree, and it is short pitched by 60 degree electrical. Suppose if the coil span is 5 slots as considered here, then coil span is short pitched by 1 slot, and coil span in terms of electrical degrees is 5 into 30 degree electrical, which is the slot angle. So 30 degree into 5 will be 150 degree electrical. So coil span is less than a pole pitch in the case of short pitched coils. So what exactly the full pitch coil and short pitch coil, how the coil sides to be placed in various slots. So that is depicted here. Suppose the same example we will take, 36 slots, 6 pole alternator, coil span is equal to pole pitch in the case of full pitch coils, that should be equal to 6 slots. That means coil side what is placed in a first slot should be connected to the coil side placed in a 7th slot, that is here. So that means whatever the coil here placed in coil side placed in first slot, that is to be connected to the coil side placed in the 7th slot. But in the case of short pitched coils, if the pole pitch coil span is equal to pole pitch minus 1, which is equal to 5 slots, then two sides of the coil occupy say first slot and 6th slot. Earlier the other coil side was occupied in 7th slot. Now in the case of short pitched coil, it is housed in 6th slot. This is about full pitched coils and short pitched coils and how the coil sides occupy various slots. Let us consider what is meant by pitch factor. So let us see, as I said earlier, this is one slot, and for full pitch coils the other coil side to be apart by 180 degree or which is equal to pole pitch. So now if the coil side is short pitched by say alpha degrees, then coil span in terms of electrical degrees will be 180 minus alpha, and say this portion of the conductor as or this portion of the coil as said earlier is called as back connection, and it is also called as overhang region. So this overhang region is mainly to connect the various conductors at the back end of the armature. And if we see for a full pitch coil, the coil side EMF of first coil side is say E1, coil side EMF of second coil side is E2, and these two EMFs are additive, so they are in phase. So total EMF of two coil sides put together will be the coil EMF or EC. So pitch factor is defined as the vector sum of coil side EMFs to the coil EMF. See, coil EMF is E1. So this is this coil EMF divided by coil side EMF is nothing but pitch factor. So pitch factor is in particular for full pitch coils is equal to 1. So that is because coil EMF is the vector sum of these two EMFs, and since these two EMFs are in phase, so the ratio between EC and vector sum of E1 and E2 is less. So we will see what happens in case the coil span is less than full pitch. Suppose if this is coil side EMF of first coil side, and for 180 degree this dotted line is the position of coil side EMF of other side of the coil, that is E2, but since coil side of other side of the coil is short pitched by alpha degrees, then this falls back by alpha degrees, and the resultant EMF, that is the coil EMF between this end and this end of the coil is now less than the arithmetic sum. So vector sum is less than the arithmetic sum. So arithmetic sum is E1 plus E2, vector sum is EC, and this vector sum is given by E1 cos alpha by 2 into 2. So we will get vector sum as 2 into E1 cos alpha by 2 divided by arithmetic sum, that is 2 E1, which is given by cos alpha by 2. So, pitch factor is again defined as it is the vector sum of EMFs of the two coil sides to the arithmetic sum of the EMFs of the two coil sides. So, if the coils are short pitched, then induced EMF is reduced by a factor of cos alpha by 2, where alpha is the short pitch angle. So, pitch factor Kp is the EMF induced in the short pitched coil to the EMF induced in a full pitched coil, and it is given by Kp, which is equal to cos alpha by 2, where alpha is also called as a chording angle or a short pitch angle. For a full pitched winding, alpha is equal to 0, and Kp, that is pitch factor, is given by cos 0 by 2, which is equal to cos 0, which is equal to 1. Let us look at what are the advantages of short pitch winding. So, in the case of short pitch winding, the advantages are we will save copper in the copper of the winding. So, let us see how exactly it is. For example, so look at here, for full pitch coil the overhang length is more, for short pitch coil overhang length is less, or the copper used for the back connection is less for short pitched coil. So, this can be directly comparable, and because of this we save lot of copper as far as the end connections are concerned. And the other advantage is it reduces the harmonics in the MMF of the armature winding. It is also responsible for reduction of EMF harmonics induced in the windings without significantly reducing the magnitude of fundamental EMF. We know that the magnitude of fundamental EMF gets reduced by a factor of Kp in case the coils are short pitched, and if this is to be compensated, we require additional turns that is to be added to the coils. Suppose 100 turns are used by the full pitched coils, then we may require say another 5% additional because of the reduction of EMF due to short pitching of the coils. So, whatever the additional copper used for increased number of turns is always less compared to whatever the copper saved in the overhang region. So, we get net saving of copper by short pitching the winding. So, let us also look at what is meant by concentrated coils and distributed coils. So, in the case of concentrated coils, suppose a coil has say 30 turns in one coil, and all these turns are placed in one slot. So, naturally the total area of the conductor what is required for concentrated coils, all these area of conductor to be housed in the slot. So, depth of the slot that is required with concentrated coils is more compared to distributed coils. So, in the case of distributed coils, say this 30 turns is divided into say 10 turns 3 coils, and these coils are housed in different slots. So, that means total turns in one coil group. So, now we will call these 3 coils together as coil group, and in this coil group there are m such coils. So, m is equal to 3 in this particular case, and m is 3, and the number of turns in each coil is given by total turns 30 say divided by m, or in general T by m. So, in this particular case T by m, since m is equal to 3, T is equal to 30. So, we will have 10 turns in each of this coil, and the depth of the slot that is required in order to house these 10 turns compared to the first case is less. So, with the distributed coils, depth of slot is greatly reduced, and reduction in the depth of slot is nothing but a reduction in the reluctance of the magnetic path. Rather, in this particular case, since the depth of slot is higher, there is a increase in the reluctance of the air gap, and we require more MMF in order to get a definite field flux that is to be produced. So, let us compare whatever the distributed coils distributed in 3 consecutive slots. So, now when you compare the MMF distribution of one coil, so that is shown in case A, and in case B it is due to second coil, and in case C it is due to third coil. And when you add all the 3 MMF distributions due to 3 sets of coil, so because all the 3 are connected in a series, so what we get is here the MMF waveform of distributed winding is more or less sinusoidal. You can see here this MMF waveform at the air gap is almost sinusoidal, and because of this induced EMF will also be sinusoidal in nature. So, if the induced EMF departs from sinusoidal, we say that harmonics are present in the induced EMF, but since this stepped waveform here because of distribution is approaching very near to sinusoidal, we say that harmonics are reduced because of distribution of windings. With the distributed windings, then what about concentrated windings? What happens to the harmonics with respect to concentrated windings? Mainly these concentrated windings, all the conductors of a given phase per pole are concentrated in a single slot as discussed earlier. They are not commercially used because of the following disadvantages. First disadvantage being they fail to use the entire inner periphery of the stator iron efficiently. Second one, they require extremely deep slots, and because of this they increase MMF required to set up the air gap flux. Deep slots also increase the armature leakage flux and increases the armature reactance, and because of this voltage regulation of the alternator increases. Voltage regulation increases means whenever you load the alternator, voltage drop for a particular load current is increased. They also result in low copper to iron ratios by not using the armature iron completely. And the last one, they fail to reduce EMF harmonics as effectively as distributed windings. So, normally we will never go for a concentrated winding, we will most of the cases we will go for a distributed windings. So, this picture will show us how the concentrated winding at the end look like, and this is the picture with distributed winding. Here effective utilization of the iron is used, here depth of slots are increased, here depth of slot is reduced. So, let us see distribution factor, how exactly this distribution factor is going to affect the total EMF. Distribution factor is defined as the ratio of EMF induced in a distributed winding to the EMF induced in a concentrated winding. It is also called as vector sum of EMF divided by arithmetic sum of EMF. So, let us not derive the relationship in detail. So, we will directly take the formula here for Kd. Kd is given by sin m beta by 2 divided by m sin beta by 2, where beta is given as slot angle, which we have already discussed, and beta is given by 180 degree divided by slots per pole. Suppose for the given example or whatever the example we have taken earlier, for a 36 slot 6 pole, slots per pole will be 6 and beta is equal to 30 degree electrical. M is given as number of slots per pole per phase. So, for a 3-phase generator, number of slots per pole will be 6 in the considered example. Per phase there are 3 phases. So, slots per pole per phase is equal to 2 in the case of 36 slot 6 pole 3 phase alternator. And for concentrated winding, as usual beta is equal to 0. So, what we get is Kd is equal to 1. So, let us consider the equation for induced EMF or EMF equation. The EMF equation of an alternator can be derived by considering the following parameters. Let Z is equal to number of conductors per phase, T is equal to number of stator turns per phase, which is equal to Z by 2. So, because 2 conductors together constitute one turn. P be the number of poles, F is the frequency of the induced EMF. To begin with, let us assume all the stator coils are full pitched, for which Kp is equal to 1, and all coils are placed in one slot. So, that means coils are concentrated. Instead of being distributed, we consider now concentrated coils and full pitched coils to begin with. And in one complete rotation of the field system, each stator conductor passes through each of the poles. So, now n is the speed of the rotor in RPM, Kd is given as distribution factor, Kp is given as pitch factor, K is the form factor, which is equal to 1.11 for a sinusoidal waveform. Phi is equal to flux per pole. Thus, total flux cut by one conductor in one rotation is given by P phi Webers. Time for one full rotation is given by 60 divided by n, where n is the speed of the rotor in RPM. So, we will get time for one full rotation is 60 divided by n seconds. Rate of change of flux by one conductor is given as d phi by dt, which is equal to P phi, the total flux, divided by 60 by n. So, we will get rate of change of flux by one conductor is nothing but EMF induced in Z conductors. So, this is for one conductor. Now, we will take what happens when Z conductors per phase are in a series. So, we will get P phi divided by 60 by n into Z. So, we will finally get phi Z n P divided by 60 as the EMF induced in Z conductors per phase. And as the frequency is given by Pn by 120, so we have to substitute this in equation 1 and we get EMF induced per phase, this is average EMF induced per phase, is given by 2 f phi z volts. So, now from this average EMF we can calculate the RMS value of the EMF induced per phase by multiplying this with the form factor 1.11. So, we get 4.44 f phi t volts as the RMS value of the induced EMF per phase. This equation, what is discussed earlier, is valid only if the winding is concentrated in one slot and full pitched windings, but practically windings are short pitched and distributed. In all such cases, pitch factor Kp and distribution factor Kd have to be considered. Thus, if the windings are short pitched and distributed, EMF per phase will become 4.44 f phi t, what is derived earlier, which is to be multiplied with the Kp and Kd. So, that means Kp into Kd is abbreviated as Kw sometimes, and Kw is called as a winding factor, and Kw winding factor is given by Kp into Kd, and Kp is pitch factor, Kd is distribution factor as derived earlier. So, in summary, alternator is an AC generator. It works on the principle of electromagnetic induction as described by Faraday's laws. Whenever a conductor moves past in magnetic field an EMF is induced in the conductor. Frequency of the induced EMF depends on speed of the rotor N and number of poles P, and this frequency is given by Pn by 120. In general, for bulk power generation, armature winding of an alternator is stationary and field poles are rotating. There are two types of rotor of an alternator. First is salient pole rotor, second is smooth cylindrical rotor. In salient pole construction, rotor poles are projected outside and is suited for low speed water wheel driven alternators. In smooth cylindrical rotor, it is best suited for high speed turbo alternators. The EMF equation of an alternator is E RMS per phase, which is given by 4.44 FIT Kp Kd volts. Kp is the pitch factor, which is given by Kp is equal to cos alpha by 2. Kd is the distribution factor, which is given by sin m beta by 2 divided by m sin beta by 2. Let us look at the video which will clearly show us the working principle of alternator and various parts of the alternator. Alternator works based on the principle of electromagnetic induction, and it has various parts, and it has mainly a stator and a rotor, and basic working principle is electromagnetic induction. According to this principle, the coil has to rotate in the magnetic field, or if the coil is stationary, the magnetic field has to be rotated. So, first is rotating coil and second case rotating field. So, this particular rotating field is used in a majority of the alternator, and it has rotor which is rotating, which produces a magnetic field, and this magnetic field is rotating, and rotating magnetic field cut across magnetic lines of force rotating, which get cut across the conductor what is provided in the stator, and this type of rotor is called as a salient pole rotor, because the poles are projected outside. And here you can see the field winding, and whenever the DC current is passed through the field winding, it produces magnetic flux, and magnetic flux produced is producing poles alternatively north and south, and this is rotating as seen in the video. And you can have a coil placed around this field, and coil is now fixed and magnetic field is rotating, and you can see the direction of induced EMF get changed when the coil is subjected to different poles. So, if the coil is subjected to north pole, then positive half cycle of EMF is induced, and if the coil is subjected to south pole, then the direction of EMF is induced. So, frequency of the induced EMF is directly related to Pn by 120, and what you can see here is this frequency is given by Pn by 120, and it depends on the speed. Suppose for a 3-phase alternator, we require 3 coils, and these 3 coils to be 120 degree with respect to each other, and the one end of the coil is shorted to form star connection, and other three terminals are for various 3 phases. So, totally we will have now 4 points, say R, Y, B and neutral, and you can see for a 60 hertz system, the speed at which this rotor should rotate is 1800, and at such high speeds there is lot of centrifugal forces acting on the rotor, and because of this we have to reduce the speed. So, normally the rotor rotates at a lesser speed with large number of poles. So, if the speed of the rotor is less and it is in the range of 120 to 400 rpm for the case of water wheel generators, you can see here large number of poles, and This is the pole core. Pole core is laminated and each lamination is insulated electrically and then riveted together, and then is the construction of a rotor, and this rotor is when rotating subjected to rotating field or produces rotating field, and they get cut across the stationary armature conductors, and this is the stator core wherein slots are provided and conductors are placed, and we require to supply DC current through this rotor field winding, and this you can see there are two brushes and two slip rings, and DC supply is provided through these brushes, and if DC supply is obtained by a small DC generator, then such a alternator is called as self excited generator. And whenever the alternator is loaded, what is going to happen is the terminal voltage is going to drop. In such a case, the terminal voltage to be kept constant using a automatic voltage regulator, and this automatic voltage regulator will increase the field winding what is flowing through the field windings, and because of increased field winding, flux is increased, and increased flux is going to increase the voltage. So, automatic voltage regulator, the field strength can be increased by applying more and more voltage, and the terminal voltage can be kept constant. And I hope you have understood through this video the working principle of alternator. So, let us consider one numerical example. A 3-phase 50 Hertz star connected salient pole alternator has 216 slots with 5 conductors per slot. The winding is distributed with the KD, this is distribution factor, it is already given here, and full pitched. The flux per pole is 30 milliwebers and the alternator runs at 250 rpm. Determine the phase and line voltages of EMF induced. So, let us see how to solve this. So, KD is given, which is 0.9597, Kp is 1 because the coils are full pitched. Total number of conductors Z is equal to number of slots into conductors per slot. So, we have 216 slots and 5 conductors in each slot. So, totally we have 1080 conductors, and conductors per phase is ZPH, which is equal to 1080 divided by 3. Why this 3? Because we have a 3-phase alternator. So, it is to be divided by number of phases. So, we will get ZPH, that is Z phase, as 360. Total turns per phase is equal to Z phase by 2, because 2 conductor constitute 1 turn, and Z phase divided by 2 will give us 180. So, turns per phase is equal to 180. So, therefore, we can now calculate induced EMF per phase, which is E phase, which is equal to 4.44 Kp Kd F phi T phase. So, when we substitute Kp is equal to 1, Kd is equal to 0.9597, it is given, frequency is 50, phi is 0.03 Webers, T phase is 180. So, when we multiply, we will get 1150.488 volts, and we know that alternator is star connected and the line voltage EL is given as root 3 times the phase voltage. So, root 3 into E phase will give us the line voltage 1992.65. Let us consider one more numerical problem, and this is the last numerical problem what we can consider for today's lecture. A 3-phase 16 pole alternator has a star connected winding with 144 slots and 10 conductors per slot. The flux per pole is 0.03 Weber and the speed is 375 rpm. Find the frequency, the phase EMF and line EMF. Assume full pitched coils. So, let us first calculate frequency. Frequency is given by Pn by 120. So, P is 16, speed is 375 divided by 120, which will give us 50 hertz. N is equal to slots per pole. So, slots are 144, poles are 16. So, we will get N is equal to 9. Slot angle, you can remember, slot angle is denoted as beta, and beta is given by 180 divided by slots per pole. So, slots per pole we have calculated here, it has 9. So, 180 divided by 9, which is equal to 20 degree electrical. M is nothing but slots per pole per phase. So, what we have is, we have 144 slots, 16 poles and 3 phases. So, we will have M, which is equal to 3. Now, we can calculate KD, distribution factor, which is given by sin m beta by 2 divided by m sin beta by 2. So, sin 3 into m is 3, beta is 20, and here m is equal to 3, beta is 20. So, if we substitute, we will get KD, that is distribution factor, which is equal to 0.9598. Total number of conductors Z is given by number of slots into conductors per slot. Here we have 144 slots and 10 conductors per slot. So, we will get 1440. Conductor per phase is equal to Z phase, which is equal to 1440 divided by 3, which is equal to 480. Now, we can calculate E phase, which is equal to 4.44 Kp Kd F phi T phase. 4.44 into Kp is 1 because we have used full pitch coils. Kd we have calculated, which is equal to 0.9598, and F is equal to 50, phi is equal to 0.030, T phase is equal to 240, and we get 1534.144 volts. As earlier, the line voltage EL is equal to root 3 times the phase voltage. So, we get root 3 into 1534.144, which is equal to 2657.215 volts. So, this is how the induced EMF E phase and the line voltages to be calculated when there is a distributed winding. And you can see, because of distribution of the coils, the EMF is marginally reduced. Suppose there is no distribution, then Kd would have been 1 and this would have been slightly increased by say about 5%. So, this distribution of winding slightly reduces the phase voltage, but not to a major extent. We can always compensate for this reduction by having 1 or 2 turns extra in each of the coil. So, this is how the numericals are taken, and I thank you for today's session, and I wish you good for the next session. Thank you.